Hi everybody, my name is Joseph Babbitt,
My name is Ivan Lopez.
and today we are going to present to you our Jivin processor. So our agenda for today is we're going to go over why Jivin, the MIPS baseline real quick, our instruction formats for our processor, our hardware implementation, and then our enhanced instructions.
Why Jivin? We wanted to incorporate both of our names into our processor, so we took the first letter of Joe's name and put it in front of my name, and that's how we got Jivin. And it's a 32-bit MIPS processor based with 8 and 16-bit vector capabilities. And with these vector capabilities, we are able to perform instructions on multiple data at once. And this is very useful for multimedia applications, such as like if we want to dim or brighten a group of pixels, rather than dimming and brightening just one pixel at a time. It's also important in DSP.
So we're going to go real quick over the MIPS baseline. It has a hardware memory architecture. It's a RISC architecture, and it has all the baseline MIPS instructions that we all implemented, along with the barrel shifter and interrupts. All right, so the instruction formats, as you can see, we have our R type, our I type, and our J type for our MIPS. But then our added instruction format is the V type, so it has the E key, 1F, and then it has our function bits down here that'll decide what vector instruction will actually be implemented, will be executed. We have our source registers RS and RT, our destination register RD, and then we have a shift amount, 4-bit shift amount, because we do implement vector shifting, which we'll go over more later. And then we do have a mode bit down here, so if the mode bit is 1, we'll be doing 16-bit vector operations, and if it's 0, we're doing 8-bit vector operations.
This is just our top level. So it has the CPU, the I/O memory, and the data memory. The data memory is 4K in memory, but is capable of 4 gigs. And the I/O memory is just like the data memory, although it has interrupt and interrupt acknowledged to simulate the interrupts.
So here's our CPU, top level. It's very dumbed down. It doesn't have all of the control lines, just to be easier to look at. So we have our inputs, our DM out. So this is our data memory into our integer data path. We have our outputs of the data and I/O mem control lines, our memory address line, and our data outline. We have our internal lines, the vector data path control lines, integer data path control lines, the IU control lines, the instruction register out. And then here, as you can see, we have our D out from our integer data path, goes back into our vector data path, and we have a VDP out from our vector data path to our integer data path, so you can pass data between the two data paths, which we'll go over more later.
How big are your vectors?
How big are our vectors?
Yeah, how wide?
Well, it's a 32-bit register, but you can do 8 and 16-bit
Okay,
vector
okay.
operations.
So this is our integer data path. We added a couple things to it. We added that demux over there. That's so we could select whether we want to store ALU out or the VDP in, which comes from the vector data path, into the register file. We also expanded the tmux to bring in VDP in from the vector file, the vector data path. And we also added the D out mux.
We'll go over more why these were added when we go into our enhanced instructions. So here's our vector data path. It's pretty simple. It's based off of the integer data path. We have our vector register file here. We're going to refer to it as vector file throughout, so just know that. So this is our vector file. It has this same mux, so you can get data from the integer data path. Then we have our high-low registers, because we do also implement vector multiplication and vector division. We have our output here, D out, and then we have our vector ALU, which we're going to go over right now. It is really just top-level implementation of a bunch of smaller ALUs. So here's one part of our vector ALU. We have 4 8-bit ALUs and 2 16-bit ALUs. These ALUs are able to do addition, subtraction, and or an XOR. And they have 8-bit outputs, and then these two, same thing, and or XOR, addition, subtraction. They have 16-bit outputs, and they're concatenated into our master mux, which decides the output of the ALU based upon the type and the function select. The other inputs to our master mux is the barrel shifter, our vector barrel shifter, and our mult out and div out, which we'll go over right now. So here's the vector ALU modules actually. So this is how we just instantiate them, just to give you a quick idea. It's pretty simple, it's just a case statement based on the function select. The only difference is the inputs and output sizes are 8 bits and 16 bits respectively.
There's our multiply. So we instantiate 4 8-bit multiply modules and 2 16-bit multiply modules. The 8-bit multiply modules get 8 bits from S and T, so the first one gets the first 8 bits of S and T, the second one gets the next 8 bits, and so on and so forth. And the same thing with the 16-bit multiplies, they get 16 bits rather than the 8 bits. And the 8-bit multiplies, their outputs are 16 bits, and we concatenate them together into 64 bits and put it through to the mult mugs. And the 16-bit multiplies output 32-bit products, and we concatenate those two into 64 bits and bring them also to the mult mugs. And we have the type bit to select whether we want to output the 8-bit multiply or the 16-bit multiply products. And that goes into the Y high, Y low mugs.
So here's our Verilog instantiation of that. Again, very similar. It's just the only difference is the output for the 8-bit is going to be 16-bit product, and the output for the 16-bit vector multiply is going to be 32.
And the divide is similar to the multiply. We instantiate 4 8-bit dividers and 2 16-bit dividers. They also get inputs from S and T. The 8-bit get the 8-bit inputs from S and T, and the 16-bit device get the 16-bit inputs from S and T. And the only difference from the multiply is they do the divide, and they also, each module outputs the remainder and the product, the quotient. And the 8-bit outputs are 8 bits wide, and the 16-bit outputs are 16 wide. And we concatenate them separately into 64 bits and put them into the divide mugs, which is then selected by the type bit.
And then here's our Verilog instantiation of it. Again, very similar. The only difference is that the output of the Verilog, the divide module, is 8 bits with the remainder and quotient, and 16 bits for the remainder and quotient. So here are all the list of all of our enhanced instructions. We do vector and/or XOR for logical instructions, vector add, subtract, multiply, and divide for arithmetic, and then we have our vector shift left logical, or vector shift right logical, and then to get data into the vector data path, we have our, we give you 2 options. You can go straight to the memory through vector store or vector load, or you can use go between the 2 data paths with move vector file to reg file and move reg file to vector file. So we're going to start really easy, just to get everyone comfortable with SIMD. Just go over how vector and/or XOR work. As you can see, you have your RS and RT registers. Splits it up into 4 8-bit fields, and/ors and XORs each field together, and puts it into the RT field. So if you're doing 16-bit, it just splits it into 2 16-bit fields, and/ors, XORs together, and puts it in the respective field. There's. So just to give you an idea, and just show how it works on the actual diagram. You have S and T come in, it'll peel off 8 bits for each, and then it'll do the and/or XOR within, and then concatenate into 32 bits out. Similar thing with 16 bits, it just peels off 16 bits for each. Right.
It's just a little test that we did. We first did Louis Ories to load it into the register file, the regular register file, and then we did MVRV to load it into the vector file. And right there, that's where we did the V and the VOR, VXOR. We ORed registers 1 and 2 together, and we stored them into R3, R4, and R5 respectively.
So we're going to go over vector unsigned add and unsigned subtract. This is a good time to bring up that our vector operations, no flags. We leave that up to the programmer.
Yeah.
So these are unsigned, and there's no carry flag, there's no 0 flag, no negative flag. So similar idea, splits it up in 4 8-bit fields, add the 8-bit fields together. Same thing with the 16-bit fields, adds them up, puts them in the destination, the corresponding destination edge. And then here's our unsigned sub. It's the exact same thing, except you're subtracting now. So how it works, all over again, you do your 8 bits addition subtractions within these ALUs here, and then 32-bit outputs for each.
And here we're adding registers 2 and 3 together using the 8-bit add and storing it into register 9. As you can see right here, there's supposed to be a carry bit going over to the next bit, but as you can see, we're only doing the 8-bit, so it does not carry over.
Right.
And the same thing with the subtracts. We're subtracting 6 and 7 and storing into register 11. And here's a 16-bit implementation. We're again adding registers 2 and 3, but this time we're storing it into register 10. And again, there's supposed to be a carryover, but it does not go over because it's 16 bits. And also the same, we're subtracting registers 6 and 7, storing into R12.
All right, so our vector multiply, it's a little bit more to explain here. So each of these has a 16-bit product. So the top 16 bits, the 16 bits from this multiplication will go into the first 16 bits of high reg. The bottom 16 bits of high reg will get this multiplication, and so on and so forth into the low reg. And then if you're doing the 16-bit multiplication, the products are going to be 32 bits wide. So it goes straight into high reg, and then the products of these will go straight into low reg. So how this works, again, we have our 8-bit multiplies and our 16-bit multiplies. So depending upon what you do, you have your 16-bit products that are concatenated together into 64-bit, and our 32-bit products that are concatenated into 64 bits.
And here we're multiplying registers 4 and 5 together, and like Joe said, they go into the high and low register. So we have to also make the vector move from high and vector move from low instructions to move them from the high and low registers into the register file, the vector file. So we use those instructions to move them into registers 13 and 14 respectively. And we also do a 16-bit multiply, multiplying registers 4 and 5 and store them into registers 16 and 17.
As you can see, because we decided to do repeating values for register 4 and 5, so that you can see here's the output for their repeat over and over again, 3A02, 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 to give you an idea of the multiplication at work. And then the same other thing up here, it just has 32-bit product, so one register is going to be the output of the first 16 bits multiplied, and the second condition for repeat again in register 17. So then vector divide, it's the same idea. They're going to have, this is going to be a 16-bit output in total, but it's split into the remainder and the quotient. The top 8 bits of this will be the remainder, the bottom 8 bits will be the quotient, the top 8 bits remainder, bottom 8 bits quotient, and so on and so forth. Then here, the top 16 bits are the remainder, the bottom 16 bits are the quotient, and then top 16, bottom 16. So again, the only difference between this and the multiply circuit is that you have the two outputs, the remainder and the quotient, for the outputs of the divide modules, which are then concatenated together to 64 bits in total.
Here we're divided the 8-bit divide, we're dividing registers 2 and 6, storing them into register 18 and 19, and dividing registers 2 and 6 again in 16-bit mode, storing them into register 20 and 21. And as you can see, we're dividing a smaller number by a bigger number, showing that the quotient is 0 and the remainder is there, as showing the remainder for each one.
All right. So now we're going to go over our shifts. So vector shift left logical, it's kind of hard to see in your head, so we decided to give an example. So how it is you have these, so again, split up into 4 8-bit fields, and we shifted them all twice to the left. So you're going to see these 2 zeros brought in on the right-hand side, and the value shifted. And then the same thing here for the 16-bit values. You have RS and RT, and they are, I mean RS high and RS the low part, and it's shifted twice, and the 2 zeros are brought in with the rest of it shifted out. And then it's the same concept for shift right logical, except this time it's just shifting right. So you see that we decided to show it shifting twice to give a better representation. So zeros brought in, and then zeros brought in down here. Because we have 4 shift bits, we can go 1 to 16 places to the left or right. So how it works is we did a barrel shifter. We made it basically another barrel shifter where it's a giant case statement with the case being the shift amount, the type, and the function select. The shift amount decides how much it'll shift. The type, whether you're going to do 8 or 16-bit, and the function select, whether you're going to do shift left or shift right, and the output comes out here with this Y high, Y low.
Here we're shifting register 1, which we loaded with all Fs. And we're shifting it to the left by 1, 3, and 7, and storing them into memory. Location C0, C4, and C8, and we're also shifting it right by 1, 3, and 7 as well, and storing it to memory location CC, D0, and D4. As you can see, we're only shifting the 8 bits, each one by the 1, 3, and 7. And same thing for the 16-bit. Again, we're shifting it by 1, 3, and 7 to the right and to the left, and storing them in the same memory location, C0 to D4, but this time we're doing it in 16-bit mode rather than 8.
All right, so now we're going to talk about how you get data actually into the vector data path and out of the vector data path. We're going to start with sending data between the two data paths. We have MVVR and MVRV. MVRV, the goal is to move the value of a specified register in the register file to a specified register in the vector file. And MVVR is to move the value of a specified register in the vector file to a specified register in the register file. So we're going to go over MVVR first. So you have data in your vector file that you want to move to your register file. So what you're going to do is it's going to be, the data that you're going to send is going to be based on the T address. It's going to come out into RT during the decode state. It's going to come out through this D out line, into this VDP line here, into this DMUX, and into the register file based upon the based on the D address, 15 to 11. And then similar thing, MVRV. This time the address is going to be RT again. So in the decode state, it'll go into RT, out through D out, and into IDP out into the register file. And it's important that we did this because we wanted to be able to give the user the ability to do they can do immediate instructions now. They can do a LUI ORI to load into the register file and then send that over to the vector file so that we essentially created pseudo instructions for you to do immediate vector instructions.
Did you ever think of just doing a LUI ORI for the vector register file? Just two new instructions, kind of stick a V in front of them. V LUI, V ORI? It would just save time, but it's just two new instructions. I mean, this is great. Explanation. I don't know if it ever crossed your mind just to have two new instructions.
We came up with this idea, and we were like, oh, that's pretty cool. So
it
we
is,
kind of
yeah.
stuck with it.
Yeah.
So it actually didn't cross our minds,
Yeah.
but it is. But then, because we liked how this worked out, how you could just do it in the integer data path and send it over. So then we have here's our verification.
And here we're just showing we're moving register 9 from the vector file to register 9 into the register file. And we're also showing moving register 1 from the register file into register 22 into the vector file.
Mm-hmm.
All right, and now here comes the big ones if you want to implement with memory. So we have vector load word and vector store word. Vector load word is to load a value from data memory into the vector file, and vector store word is to store a value in the vector file in a specified address of data memory. So we're going to start with vector store word. So it's a little complicated. We're going to have to move between the two data paths, but how it works is RT is going to specify the data you want to load, that you want to store into memory. So it'll be in the decode state, it'll be RT, and then the address that you want to write it to is going to actually have to come from, whether you're reading or writing, the address is going to have to come from the integer data path.
Right.
So it's going to be passed into RS. And then on the next clock cycle, RT will come out of D out into this VDP in here and into RT, and RS will be past S. We'll use the pass S instruction to go into ALU out. So this isn't like the MIPS store word load word where you can add an immediate value to better specify your address. It's just the address that's here is where it's going to write to.
Got it.
So then on the final clock tick, ALU out will go to the memory, and RT will come out and store the data in that
Store the
memory
data.
location.
Excellent.
And then we have our load word. Our load word is the same idea. The address that you're going to read from comes from the integer data path. It comes out of RS, do a pass us to the ALU, and then out to memory, and then it'll come into DN. DN will then output out through this MUX, into this MUX, and into our register file here. So that way you can load and store word.
Here's the little verification that we did. So we're trying to store the first two words from memory. So first we have to put the memory address into register 15, 00, and then from there we did the load word, the vector load word, to store it into register 1. Then we have to do a add immediate on register 15 to increment to the next memory address so we can store the next word into register 2. Here's a vector to store word, where we're just storing register 2 into the memory addresses of C0 to C8. Again, we have to do an add immediate by 4 on the register 15, which has the memory address, so we could be able to store into the next memory addresses, which are C0, C4, and C8.
Got it.
All right, and that ends our presentation. Thank you for your time. Any questions?
I've got a question. Was that not fun when you got it to work?
Yeah, that was cool.
That
It
was really cool.
It was very satisfying.
Yeah.
To work, yeah.
No, you did a great job. Excellent. Thank you, guys.